Good evening, dear all. Today, let us study the forces due to multiple charges based on the Coulomb's law. Multiple charges is a combination of many charges Q1, Q2, Q3, so on, Qn. Let us place out of these three charges, two charges which are affecting a third charge. So let us consider Q1 being affected by the forces of Q2 and Q3. Now, as I said, all these charges are positive. So, let us write them as positive. And as I said, that let us consider the force of Q2 and Q3 on Q1. Now, if all are positive, then all of them will push each other. All of them will repel from each other. So, if they are repelling from each other, they have to go far away from each other. Okay. So, let us consider the push of Q2 on Q1, that is the repulsion between Q1 and Q2. Right? Again, let us consider the push of Q3 on Q1. So, now let us understand how to find out the total force of a repulsion which is acting on the charge Q1 by the principle of superposition, which says that when there are two or more forces acting on a single charge, they have to be added one by one vectorially. So, for calculating the force on Q1, we have to write F1 vector is equal to F12 vector plus F13 vector. That is the force on Q1 due to Q2, and this is the force on Q1 only due to Q3. Force of repulsion, because both are positive charges. Okay, so let us write using Coulomb's law. F12 is equal to K Q1 Q2 upon the distance between the charges 1 and 2 given by R12 square R12 cap. So let us write that vector here as R12 cap. That gives us the direction of the force F12. Similarly, let us write F13 is equal to K Q1 Q3 R13 square R13 cap. So let us write the unit vector R13 cap, which is between Q1 and Q3. So according to the principle of superposition, now we have to add them for finding F1 vector, which is equal to K Q1 Q2 upon R12 square R12 cap plus K Q1 Q3 upon R13 square R13 cap. Similarly, if I have n charges, one more charge Qn here, one more charge Q4 here, let me have n number of charges. I just have to find out the addition of all these forces on Q1 and add them vectorially such that the total force on F1 on Q1 due to Q2, Q3, Q4, Qn is given as K taking common, Q1 taking common, as it will be there in every term. We can write KQ1 Q2 upon R12 square R12 cap plus Q3 R13 square R13 cap plus so on Qn R1n square R1n cap, where R12, R13, R1n are the unit vectors of these forces, and R12, R13 and R1n are the distance between these charges. Okay, so writing the formula for the total force acting on the charge Q1 due to all these charges, we can say K Q1 sigma, which is a symbol of summation, I is equal to 2 to n because our charge is starting from 2. So we are writing from I is equal to 2 to n qi r1I square r1I cap, where I is equal to 1 to 2. So this is the total force acting on the charge q1 due to q2, q3, q4, so on qn. Now how to add this vectorially? We have to use the parallelogram law of forces which we learnt last year and find out the resultant of these forces. So let us name this as F13 vector, F12 vector, such that the resultant of these two forces is F1 vector. F1 vector. Okay, so if we find the resultant of F12 and F13, we will get F1. This is the answer of the force acting on the charge Q1 due to Q2 and Q3. Similarly, if we want to add for the forces acting due to Q2, Q3, Q4, Qn, we have to follow the same method of vectorial addition. Okay. So continuing the concept of forces due to multiple charges, let us consider a numerical based on the concept, which is going to work on the principle of superposition. What is the principle of superposition? To find out the total force acting on one single charge, we have to add the other forces vectorially, considering each force separately. Okay, so let us first read the numerical. What is given to us? It is given to us that consider three charges Q1, Q2, Q3 equal to Q, which is written here by me, at the vertices of an equilateral triangle of side L, and because it is an equilateral triangle, we can say that each angle is 60 degrees. Okay, so what is the force on the charge Q, which is placed at the centroid? It is also given that Q is also positive, or Q is also of the same sign, whether positive or negative. All are either positive or all are either negative, which is given to us in the question. Now the question is, what is the force on the charge Q placed at the centroid? So now looking at the geometry of the figure, first we have to understand where or what are the forces acting on the charge Q at the centroid. So what are the forces? The forces are from A, that is the charge Q, to O, that is the charge Q. So the direction of this force is downwards, F1, given by F1. Similarly, we have from B to O, that is from B, Q to O, Q, the direction of the force is F2. Similarly, we have the charge on C, that is Q, to the charge on O, that is capital Q, the direction is F3. So F1, F2 and F3 are three repulsive forces acting on the charge Q placed at the centroid. These forces are repulsive only because all the charges are of same sign. Okay, so let us use the superposition principle and write down the total force on the charge at the centroid given as FQ. Let us denote it as FQ is equal to F1 plus F2 plus F3. Now our work is to add them vectorially, right? So first let us find out the magnitude of F1, which is equal to K Q upon OA square, because OA is the distance between Q and A. Similarly, F2 is equal to K Q OB square. F3 is equal to K Q OC square. Now, as can be seen, we don't know the value of OA, OB and OC, which is the distance from the centroid to the vertex. So let us consider this triangle ODC. From this figure, we can name this portion DC as L by 2. Okay, and we just redraw the triangle OCD, which is just the same as this OCD here, and find out the value of OC. which is given by trigonometric ratios as DC upon cos 30 degree. DC is L by 2 as can be seen, and cos 30 is root 3 by 2 as we know. 2 cancel, we get here L upon root 3. So what is OC here? OC is L upon root 3. OC, OB and OA are equal, again given by L upon root 3. So we have the value of F1, F2 and F3 provided we substitute OC, OB and OA in these expressions once we found out the value as L by 3. Now let us add the forces on the charge q placed at the centroid vectorially. So let us consider these two vectors F2 and F3 as two sides of a parallelogram such that their resultant is the diagonal. Let us finish this parallelogram, complete this parallelogram such that the resultant of these two forces is through the diagonal passing through the vertex of these two forces. So looking at the diagram, we can find out using the parallelogram law and naming the force as F1 dash. Let us name this as F1 dash. F1 dash is equal to root of F2 square plus F3 square plus 2 F2 F3 cos 120. As can be seen from the figure, this angle here is 120 degrees. As can be seen in this figure also, the angle between F2 and F3 is 120 degrees. If this is 30, this is also 30, then this is 120. Vertically opposite angle, the opposite vertically opposite angle is also 120. So this is 120, so that is also 120. Let us substitute here 120 as the angle between the two vectors F2 and F3, such that we can write F is equal to F2 is equal to F3 as can be seen from the magnitudes. So F1 dash, which is the resultant of F2 and F3, is equal to F square plus F square plus 2 F into F, which is again F square, multiplied by negative half. So my answer here is F1 dash is equal to root of 2f square minus f square, which is equal to root of f square, which is equal to f itself. What is f? F is f2 or f3, which is given as k q upon OB or OC, which is given to us as L upon root 3 square, which is equal to k q. I take it up as, so that is 3 upon L square. Now I rewrite F1 dash as 3 q upon L square, where I have written the reciprocal of the denominator. We leave this here and we have got the resultant. So we have got this resultant, right? Now there is a third force which we have to add to the resultant of these two forces. But as can be seen, the resultant of these two forces is upwards and F1 is downwards. So the directions of these two forces which is available to us is opposite in direction, as can be seen from figure. So let us see what is the magnitude of F1 now. So what is the magnitude of F1? That is, substituting the value of OA square, we get k q upon what is OA? L upon root 3 whole square, which is again by inverting the denominator, we get 3 q upon L square. So let us name this equation 1. Let us name this equation 2. As can be seen from equation 1 and 2, the magnitude of F1 dash is equal to F1. But what about the directions as seen from the figure? Both the directions are opposite and their magnitudes are equal. So if I write the vector, then I write it negative F1 dash. So finally, the force acting on the charge capital Q placed on the centroid is equal to 0 because F1 dash and F are equal in magnitude and opposite in direction as seen from equation 1 and equation 2. So let us continue with the numericals based on the forces due to multiple charges, and we shall do a textbook numerical. In this numerical, there are again 3 charges which are having different polarities. So let us read the question, right? Okay, consider the charges Q, Q and negative Q placed at the vertices of an equilateral triangle as shown in the figure 1.7. What is the force on each charge? So the question here is, what is the force on each charge? That's the question. Okay, so now we can see that these 2 charges Q1, Q2 are both positive and Q3 is negative. Now we have to be very careful whenever the forces between 2 charges are asked. We have to understand what is their polarity. Only then we can proceed with a numerical such that we understand the direction of force exerted on one charge due to the other. Is it attractive? Is it repulsive? Then our nearly half of the numerical is solved. So let us find out the direction of force exerted by each charge on each charge. Okay, so let us consider first the vertices A on which there is a charge Q which has forces due to the charge on B, that is Q, and force due to charge on C, that is minus Q. So let us first consider, are these two forces acting on A repulsive or attractive? So these 2 forces are positive. Sorry, these 2 charges are positive, so the forces on them will be definitely repulsive. So we have a repulsive force on A due to the charge on B. At present we are interested in only A, so I am writing or drawing the direction only for A. Now the force due to the charge on C is which is acting on A is understood by the polarity. So one is positive, this charge is negative, so there will be a force of attraction between these 2, right? So you can see the arrow from here to the arrow from here. So I got the direction of F13 and F12. F12 is the force on Q1 due to Q2, and force F13 is a force on Q1 again due to Q3. This force is attractive as you can see. This force is repulsive as you can see. Now let us find out the forces on the charge Q2, which is having the magnitude Q. So again here I focus on this point and understand that these 2 forces are again positive. So these 2 forces will repel. The force exerted by Q1 on Q2 will be repulsive. Correct? So denoted by F21, force on 2 due to Q1. Similarly, let us decide the direction of force due to Q3 on Q2. This force will be attractive because the polarity of the charge on C is negative and the polarity on the charge B at B will be positive. So you can see the attraction between these 2 charges. Okay, so here we have the attraction between these 2 charges. Here we are ready already. We need not again say, but once let me finish it, that the force on Q3 is due to Q2 given by this direction. Force on Q3 due to Q1 is given by this direction. So all the forces acting on each of them is shown. This is the first work you have to do. Determine the direction of forces acting on each charges depending upon the polarity of the charges. If both of them are positive, they will repel. If both of them are negative, also they will repel. If one of the charge is positive, if one of the charge is negative, they will attract, as you can clearly see here. Okay, so these 2 are repulsive, these 2 are attractive, these 2 are attractive because one is positive, one is negative. One is positive, one is negative. Here both are positive, so they will repel. Done. Now, what is our next step? To find out the resultant force direction on each of the charges. So, first again we will come to the charge Q1. What can be the resultant of these 2 forces? According to the parallelogram, again through the diagonal of the parallelogram formed, we can even complete the parallelogram here, but there is no need. Correct? Similarly, what is the resultant here on Q2? Here, it is again the diagonal between these two adjacent sides of a parallelogram. Okay, so this is F2. This is F1. This is F2. Now here, what is the direction of the resultant? Downwards, again using the parallelogram law of vector addition, where you draw a diagonal between the two adjacent sides of a parallelogram. So we are done with the directions of individual forces and the resultant force. We are ready with the direction. Now what should we do? We have to just find out the magnitude of each force acting on each charge and add them vectorially. We are done. So let us first consider the force F1 is a vector addition of F12 vector plus F13. Similarly, F2 is a vector addition of F21 plus F23. And F3 is a vector addition of F31 plus F32 vectors. So all these forces are the vector addition of their component forces that is seen. Now let us go to their magnitude. We'll just write the magnitude of F12. What is the magnitude of F12? Where is 1? Here. Where is 2? Here. What are those charges? K. First charge is Q. Again Q. Here. And then distance between them as shown is L. So L square. Now when we are writing the magnitude, remember that we should never multiply the polarity, because already we have considered the directions. So do not multiply the polarity for negative charge Q. So as can be seen, all the charges are having the same magnitude Q, Q, Q. Distance is also same L, L and L. Correct? So the magnitude of all these forces which are seen here will be same. F13, I am only writing magnitude, that's why I am not writing the F. F13 is equal to F21 is equal to F23 is equal to F31 is equal to F32. So here I am ready with the directions. Here I am ready with their magnitude. Correct? So I am ready to find out the resultant force F1, F2, F3 using the parallelogram or a parallelogram law of adding the vectors. Fine. So let us first find out F1 is equal to root of, as it is written here, let us write the common force F for all these forces. So I can write here F12 square plus F13 square, as can be seen from the given vector addition, to F12 F13 cos 120, because as you can see here, if this is 60 degree, then the other portion 180 minus 60, 120 degree. This is the angle between the two vectors F12 and F13. Right? This is the angle. Fine. So I have written cos 120 degrees. Similarly, if I go to the force F2, the angle between these two vectors is again 120 degree. The magnitudes also, as you can see here, are same. So I'll get back to that. So what do we have here now? As written, every magnitude is equal to F. So I'll write here F square plus F square plus 2 F into F, F square. Cos 120 is negative half. So what do I get? 2 cancel. I get 2F square minus F square, which is equal to root F square, which is equal to F. So my F1 magnitude is F. Similarly, if I look at F2, angle is the same between the two forces acting on F2, acting on Q2, and the resultant is diagonal to the two sides of a parallelogram, the two sides or the two adjacent sides of the parallelogram, again making an angle of 120 degrees between the vectors. So same answer I shall get even for F2. So I can write the magnitude of F1 is equal to F2 is equal to F. So this is the magnitude of the resultant force at Q1 and the resultant force at Q2, which is equal to F. That is mentioned here, as you can see. Okay, now we go, as the question goes, find the force on all the charges, on each charge. So let us find out F3 now. So for F3, again we write F31 square plus F32 square plus 2 F31 F32 cos 60 degree. Why did we write 60 degree here? Because the angle between F31 and F32 is 60 degrees, as this is shown as an equilateral triangle, given as an equilateral triangle to us already. So let us substitute the values of all these forces and the angle, and that we get F square, as I already mentioned there, all these magnitudes are equal to F, plus F square is equal to plus 2F into F, again F square, and cos 60 is half. So 2 to cancel, what do I get here? Root 3 F square, which is how much? Root 3 F. Root of F square is F. So F3 is F. So here I have the value of F1 is equal to F2 is equal to F, and F3 is equal to root 3. F3 is equal to root 3F. Okay, so here, as written here, F3 is equal to root 3F. You can even write modulus because that is the magnitude, right? Okay, so looking at the diagram and the result we have calculated all the three forces on all the three charges Q1, Q2 and Q3. Now here we can extend our question by ourselves, and we can ask what is the vector addition of F1, F2, F3. Can we do that? Yes, we can. So let us first draw the direction of F1. I have just copied this direction. Okay. Similarly, draw the direction of F2 as seen here. What is the direction of F3? Downwards, as seen there. Okay. So again, by the parallelogram law, I can find out the resultant of F1 and F2, which is the diagonal of the parallelogram formed with F1 and F2 as their sides. As you can see, I can get one F dash, and F dash will be equal in magnitude and opposite in direction compared to F1. Hence, the two forces F dash and F3 will cancel out each other. It means that F1 plus F2 plus F3 vector is equal to 0. I hope you have understood that when there are multiple forces acting on a body, you just take 2, 2, 2 as a pair, use the parallelogram law, find out the resultant and add those resultant again. That is the way of finding out the forces acting on a system or on a charge. This is a force acting on a system, which is understood that the force acting on the system of these three charges is 0. This question is not asked, but we can do it as a self question. Okay. Okay. So let us consider forces due to multiple charges. Now at present we have in this numerical 4 charges. So let us read the numerical and understand what they have given. Two opposite corners of a square. So I have drawn a square ABCD. Opposite corners of a square carry Q charge each. So Q and Q, opposite vertices of a square, and the other two opposite corners have the same square of the same square carry Q charge, that is small q on the opposite vertex of the square. If the resultant force on Q is 0, now here they have given Q, so I can consider any of the two charges, small q or this small q. Okay, so they have already given me that the resultant is 0, right, on Q. So we will consider that the force is on one of the charges, small q, the resultant is 0, that is given to us. So how are Q and Q related? That is a question asked. So for any such type of question, our first work is to understand that what are the forces acting on the given charge. At present, our given charge is this Q or this Q. We are selecting that Q. We can also select this Q. And they also have given us that all of them are positive because nothing is mentioned about polarity. You can take it as positive. So all charges are positive. Fine. So let us first understand what are the forces acting on Q. So from this vertex A, capital Q, to the vertex D, small q, both are positive. So both the forces, both the charges will repel. So I draw this force on Q due to this Q, which is repulsion. Similarly, the force due to this charge on this charge will again be repulsion because both are positive. So I draw it from here, repelling. Okay, these are repelled, but we are not interested in these directions. So I haven't drawn. Need not confuse and need not draw also. Now, what is the force between this Q and this small q there? Again repulsion. Why? Because these charges are again positive. So they will repel each other. Fine. So I have three forces acting on this small q. Let me denote them as F1, F2 and F3. These are the three forces which are acting on the charge Q due to the availability of the other three charges on the vertices of a square. Correct? So applying the principle of superposition, the charge on Q can be written as FQ. FQ is equal to F1 plus F2 vector plus F3. Let us first find out their magnitudes. We already have the charges. To find out the magnitude, we must know the distance between these charges. So let us write the distance between these charges as L for this pair and L for this pair. The other pair is also L and the other pair is also L. But what is the value of the diagonal for a square? This is a square. So what is the diagonal value? So we can use the Pythagoras theorem here and find the value of BD. So just a small calculation, that is L square plus L square under root is equal to BD square is equal to BD. So that is root 2L. So we have BD is equal to root 2L. Let me write it here as the length of the diagonal of the given square with equal sides L. Fine. So we can use these distances between the charges here and write the value of F1 is equal to K. Capital Q, small q, because F1 is between, force is between capital Q and small q, Q upon L square. Similarly, for F2 also, as you can see, the charges are the same, capital Q and small q, distance is again L, so the force F1 and F2 magnitude is the same. Now come to F3. F3 is equal to K, as you can see here, from small q to small q, and the distance between these two charges is root 2L. So let me write Q upon root 2L the whole square. So what is my answer? KQ square upon 2L square. So I am ready with the magnitudes of F1, F2 and F3. And as the question is asked, the resultant on the charge Q is 0. So now I should find out the resultant of these three forces. Correct? So what is the resultant of these three forces? Let us find out that. Okay. So as the question says is that the resultant on the charge Q is equal to 0. So F1 plus F2 plus F3 is equal to 0. Okay. So as seen here, we can find out, or we can just substitute as what is given to us, and we have to find out a condition between capital Q and small q. So it can be written as F1 plus F2 is equal to minus F3. That means the resultant of F1 plus F2 is opposite and equal to the vector F3. Fine. So by adding these two vectors F1 and F2 by the parallelogram law, we can write one force as the resultant of these two vectors, just denoted by F1 dash, which is equal to, again, as we have seen, the both are equal, so just write it as F. So I can write it as F square plus F square plus 2F F cos 90. Reason, the angle between the two vectors F1 and F2 is 90 degrees, right? So we substitute here 90 degrees as the angle between these two vectors, where I have substituted F1 is equal to F2 is equal to F. So we have here only 2F square as cos 90 is equal to 0, right? So my answer goes to F. Now this F1 dash is the resultant of F1 and F2 as vectors. Now as per the question, we equate the magnitude of these two forces, that is F1 dash is equal to negative F3, right? So substituting the values of F1 dash as root 2F and F3 as given here, we write down 2 root F is equal to negative F3, that is 2 root 2 F. What is the value of F? K Q upon L square is equal to negative K Q square 2 L square. Now we cancel L square, K and K, Q and Q left out with root 2 Q, capital Q is equal to negative Q upon 2. Therefore, we get Q is equal to Q upon 2 root 2, or small q is equal to negative 2 root 2 capital Q. Fine. This is the condition for the forces acting on Q to have a zero resultant as given in the question.